Hi, I'm Andrew Komasinski, and this is the 8th flip in a critical thinking course. This is the 7th that is being assigned as homework. So far, we have looked at rules for general arguments. We have talked about making arguments clear by making them concise, consistent, and concrete, and also avoiding using emotional language and attempting to put them in a good order with a clear set of premises and a clearly placed conclusion, either at the top or the bottom. In addition to that, we've started looking at deductive arguments. So far, we have looked at Aristotle's 3 laws of logic. We have looked at the concept of validity, and we have looked at using truth tables and operators to show whether something is valid. I'm going to briefly review some of those concepts today, and then I am going to show you how to use the short circuit method to save time when evaluating these arguments. So to review, a valid deductive argument is one where if its premises are true, its conclusion must be true. So every time that we can make the premises true based on the truth of the variables, the conclusion must also be true. If this is the case, we would say this is a valid deductive argument. This type of argument is also truth-preserving. They accomplish this by using a limited number of operators, things like and, or, and if-then, and by following the 3 basic laws of logic. So, what are those 3 laws? Those 3 laws are the law of non-contradiction. A and not A cannot both be true at the same time with the same meaning. The law of the excluded middle, which is that of A and not A, only one of them can be true at any given time, and only one of them must be true. Law of identity, that A has the same meaning every time that we're using. So we also had some standard argument patterns. We had modus ponens, which is if P then Q, P therefore Q. Modus tollens, which is if P then Q, not Q, therefore not P. We also had disjunctive syllogism, A or B, not A, therefore B. We had hypothetical syllogism, if P then Q, if Q then R, therefore if P then R. Finally, we had dilemma, A or B, if A then C, if B then D, therefore C or D. Or in another form, A or B, if A then C, if B then C, therefore C. Actually, longer form, therefore C or C, but C or C is the same thing as C. So we also had some standard operators. So I talked to you about negation. So negation, we have P, and the negation of P is not P. So negation works on only one thing at one time. It takes something that is true and makes it false, and something that is false and makes it true. So this is the way that negation operates. We had conjunction. A conjunction is something where we have 2 variables. We have, let's say, P and Q. Conjunction is true only when both are true. So it's true when P and Q are true, but it's false every other time. We had a conditional. A conditional is true if the left side is true and the right side is true, or if the left side is false. Then it's always true. A conditional is false when the left side is true, but the right-hand side is false. A disjunction is true when either side is true. So this is an inclusive disjunction. So this is A or B. If A is true, it's true. If B is true, it's true. If both are true, it's still true. If we had an exclusive disjunction, then it's only true and one of them is true. But we're not using that in this class. I only mention it because it helps some people to understand. Proving validity. If the premises are true, then the conclusion must be true. This means we have a relationship somewhat like the conditional table. So I put the conditional table up over here so that you can look at it one more time. But how does that work? When we're testing for validity, we start by looking at cases where every premise is true. Then we see if the conclusion could ever be false. If there's any time when all of the premises are true but the conclusion is false, then the argument is invalid. If there are times where all the premises are false and the conclusion is false, we don't care. If there are times where all the premises are true and the conclusion is true, that's useful, but that actually does not affect whether it is valid. We only want to know, can we ever have all true premises and a false conclusion? How do we do this? We use truth tables. A truth table shows every possibility of true and false for all of the variables of an argument. Thus, it can show us every way to get all true premises and then whether the conclusion is true or false. A truth table is an exhaustive method, meaning it does everything that you have to do to get to the answer. It will give you every single row, even the ones we don't need. So here's the one that I gave last time. Either I will play power grid or I will play Carcassonne. I will not play Carcassonne, so I will play power grid. Then I presented 5 different steps that we will take to get to the truth table we want. We want to identify the premises and count them. We want to identify the premises and the conclusion and count all of them together. Then we want to identify and count the number of variables that we used in our argument. Every different claim is going to be a variable. Finally, we want to make a table with one column for each variable, premise, and conclusion. So if we had two variables and we had two premises and a conclusion, we need 5 columns. Then we're going to write the names of these at the top of each of these columns. And then we need rows based on the number of variables. If we have two variables, each thing can be true or false. So we have 2 variables times 2 possibilities is 4. If we had 3 variables, then we have 2 times 2 times 2, which is 8. Here's an example of how this would look if we had 3 variables. So I've given us 8 rows, and if we had 2 premises and a conclusion. Then we would fill these things in using our tables. So this goes back to our idea for validity. Our test for validity is that we check every place where all of the premises are true and see if the conclusion could be false. If that is ever possible, regardless of whether these things are true or not in this world, then our argument is invalid, meaning it does not guarantee that if we start with true premises, we will get a true conclusion. Let's get some practice doing this. So here are our 5 arguments. P implies Q, therefore not P or Q. 2. A implies B, ergo B implies A. 3. A and B, therefore A or B. 4. A implies B, B implies C, therefore not A or C. 5. Not P or Q, not P and Q, therefore X. So I'm going to show you how to do this for each of these 5 arguments. Let's go. First argument, so we have P implies Q as our premise, therefore not P or Q. First step, identify the number of premises and count them. Second step, identify and count the number of variables. Third step, make a table with one column for each variable, premise, and conclusion. Fourth step, write the variable, premise, or conclusion at the top of the column. Finally, add rows based on the number of variables. So I'm going to do this one in a couple of steps. So I have one premise, P implies Q, one conclusion. I have 2 variables, P and Q. This means I will have 4 columns. So we'll write these at the top. How many rows will I have? The answer is I will have 4 because I have 2 variables. So we're going to get a table that looks like this. We'll place the variables on the left. Next, we'll put the premise. Finally, we'll put the conclusion. All right, so I just filled this in very quickly. So I'm going to walk us through this so that we can do it together. So the variables on the left, the one most left, we do TTFF, then we do TFTF. The premise, we're going to fill out using the table, but let's just wait a minute and we'll get back to that. The next thing I did was add a helper row. So since our conclusion involves not P, it helps a lot of people to make an extra column to talk about not P. So not P is just the opposite of P. So everywhere that P is true, not P is false. So that means that we have FFTT for that helper row. P implies Q. P implies Q. So here we have TFTT. Why? Because the top one, it's true, true, therefore true. The second one is true, false, and that is false. The third and fourth, the left-hand side is false, so that means it's automatically true. Then we can look at our conclusion. So our conclusion is an OR. Anywhere that one side is true, the entire of that conclusion is true because it's OR. So we have true or false, true. False or false, false. True or true, true. True or true, true. So what that told us is if we look at our premise, everywhere that our premise is true, we need to check, is our conclusion also true? So in the first row, our premise is true and our conclusion is true. In the third row, our premise is true and our conclusion is true. In the fourth row, our premise is true and our conclusion is true. We don't need to check the second row because our premise is false. So it doesn't matter for whether it's valid. So this is a valid argument. This actually has a name. This is called material implication and is one of the most basic concepts used in doing logic. You don't need to know that name for this class, but it's interesting to see that different things by appearances are actually the same thing. So P implies Q is the same thing as not P or Q. Let's go to our next one. So here we have again, A implies B, ergo B implies A. So we need to identify the premises and conclusions and count them. So we have one premise, one conclusion. Identify the variables and count them. We have A, we have B. Write the variables, the premises, and the conclusion at the top. So we're going to need 4. And then we again have 2 variables, so 4 rows. So we have 4 columns, 4 rows. So let's look at how this goes. So the part on the left is again going to be the same. TTFF, TF, TF. We always write this in the same order. Don't worry about that. Then we have A implies B. So in order to do A implies B, we can use this conditional table that we have here. So we have P and Q. So we just fill that out. So we have, for the top one, A, B, so it's T. For the next one, we have true, false, so it's false. For the third one, we have false, true, so it's true, and then false, false, so it's true. Now let's go to the conclusion. Now it's backwards, so we need to read them with B being the one on the left. So when B is true and A is true, it's true. When B is false, it's going to be true. When B is true and A is false, it's false. And when B is false and A is false, it's going to be true. So now let's check. There are 3 places where our premises are all true. 1, 3, and 4. When we check the conclusion, in row 1, the conclusion is true and the premise is true. When we check row 3, the premise is true, but the conclusion is false. When we check row 4, the premise is true and the conclusion is true. But because in row 3, the premise is true, but the conclusion is false, this is an invalid argument. All right, let's look at another one. So this time we have one premise and one conclusion. We have 2 variables, we have A and we have B, and we're going to need 4 columns because of that, and we have 2 variables, so we need 4 rows. So what do we do this time? So again, TTFF, TF, TF. Then we need to look at the table for A and B, which is conjunction, and we need to look at the table for A or B, which is disjunction. So we can use that to fill out the top. So A and B, where they are both true, it's true, and everywhere else it's false. So for our premise, it's T, F, F, F. Then we can look at our conclusion, A or B. Looking at disjunction, this is true everywhere except where both of the parts are false. So we're going to get T, 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 F. So we only need to check one row. The reason why is we only have one row that has a true premise, which is row 1. So here we have a true premise and a true conclusion. This enables us to say that A and B as a premise with A or B as a conclusion is a valid argument. So this seems strange because there are places where A or B is true, but A and B is false. But we don't care. The question is, if the premises are true, will the conclusion still be true? Let's look at one more. A implies B, B implies C, therefore not A or C. So in this case, we have 2 premises and 1 conclusion. So we have 3 of those sorts of rows, and we have 3 variables. So we are going to need 6 columns, and because we have 3 variables, we are going to need 8 rows. So let's look at what that turns out to be. So when we had 2, we did T, T, F, F, T, F, T, F. With 8, we do T, 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 F, 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 F. Then we do T, T, F, F, T, T, F, F, and then T, F, T, F, T, F, T, F. So now we need to also think about that conditional chart. What does that do? When we think about the conditional chart, we get T, T, F, F, T, 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 T. The last 4 T's are because the left-hand side is false. The first 2 T's, we have a true left-hand side and a true right-hand side. The 2 falses, we have a true left-hand side but a false right-hand side. So B implies C. So now we're going to get TF, TT, TF, TT. So again, anywhere that B is false, it's automatically true. So the 3rd, the 4th, the 7th, and the 8th rows all tell us that this premise is true. The 2nd and the 6th rows, however, have a true left-hand side and a false right-hand side. They're going to be false. So now we can check. When we check, what we're going to see is that this is actually a valid argument. So how do I know that? So the places that have both true premises are row 1 and row 5 and row 7 and row 8. If you look, the conclusion in all of these is also true. Therefore, this is a valid argument. Let's look at a fifth and final one. Not P or Q. Not P and Q. P and Q in parentheses in the second premise, therefore X. So we have 2 premises and a conclusion, and again 3 variables. So we need 6 columns, and then we also need 8 rows. What is this going to look like? So the left-hand side, you can just do the exact same thing. You never need to think about the variable part. All you have to do is make the leftmost variable half T, half F, and then split it down until you get to TF, TF, TF for the last variable. So not P or Q. Let's look at that column. So that column is going to give us TT, FF, and then all T's. Why? Because P is false from 5 through 8. Not P and Q in parentheses. So that is going to be true wherever P and Q is false. So P and Q are both true only in the first 2 rows. So that's going to give us this table. So if we look, we have a lot of places where we have all true premises. We have all true premises in the 5th, 6th, 7th, and 8th rows. 2 of these rows are very important. The important rows are the 6th row and the 8th row. They're important because in these cases, the premises are true, but the conclusion is false. This shows us that this argument is invalid. That means even if our premises were true, it does not guarantee that our conclusion is true. Now, this is really hard. It's very difficult to use this method to solve all of the problems because using this method is very, very time consuming. That is the reason why computers and other devices, when they are solving logic problems, do not use this method. Instead, they use the short circuit method. Humans use either the short circuit method or they use a kind of proofs method, which we won't go over in this class. What is the short circuit method? Let's think about it this way. The goal of a truth table is to test the validity of a deductive argument. An argument is invalid when all the premises are blank and the conclusion is blank. This means that we can actually do something to save time. The blanks are when all of the premises are true and the conclusion is false. This means we don't need to fill out the entire table because we only care about those rows where the conclusion is false and all of the premises are true. Using the exhaustive method, we filled out everything and then we looked at the end and figured out why. With this method, we're going to start from the end. So validity. Validity, if the premises are true, then the conclusion must be true. So we can start by making the conclusion false. Then we see if we can ever make all the premises true, following the rules we learned. If we can do this, the argument is invalid. So the other method, we made the entire table, looked where all the premises are true, saw if the conclusion was false. This way, we're going to make the conclusion false and see if we can make the premises true. We're going to look backwards. We're going to see, can we find a case that shows that it is invalid? So I'm going to give you an example. So we're going to start with this, A or B and C. Not B and C, therefore A. So how do we test this? We start by putting the conclusion to false. Then we already know something. We know the variable A is going to be false. After that, let's see what we can do. To make the premises true, we should start with that second premise. The second premise being A or B and C. The only way to make this true is to make both B and C true. So I've given us a helper row. So if we fill that out, the only way to do that is to make B and C true. If B and C is true, then we can check and see whether or not both of our premises are true. So the answer is going to be this. The premise A or B and C, we're going to make that true. That's fine. But if we do that, the premise not B and C is automatically going to be false. So this will show that this is a valid argument. So let's see if we can do that with a few more examples. So if we had the argument not Z implies A, not A implies D, therefore Z or D. In this case, we would start by setting Z or D to false. This would tell us that both Z and D are false. Now, if both z and d are false, this tells us something. So if we're looking at it, so we have not z implies a. We know that z is false. Not z, therefore, is true. This means to make this premise true, a must also be true. Because otherwise we'd have tf, and that's f. So we need tt in order to get this to work. Once we have true implies true, we know that a is true. Now, for the next one, we know that a is false. That means that we have the second premise, not a is false. So that means that we know that the next premise is automatically going to be true. So we are able to generate all true premises and a false conclusion. So number 6 is invalid. Let's look at number 7. So x implies not p, p implies z, p therefore not x. So we have a conclusion. So we are going to start with that conclusion. We're going to make not x false. This means x is true. So again, we're going to look at the top premise. X implies not p, and we know that x is true. In order for this to be the case, we need not p to also be true, because if not p is false, this premise is false. So if x is true and not p is true, that means that p is false. So now we can go straight to the third one of these premises, and we can see that this argument is going to be valid. Because these two premises, 1 and 3, cannot both be true while the conclusion is false. So I hope this makes some sense. So I'll do another one for you. A or B? B implies C. A implies D, therefore D. So what do we think? We are going to start by making D false, because this is our conclusion. Once we have made D false, we can look at the chart for conditional and we can go to number 3. So if D is false, if we have A implies D and D is false, the only way this can be true is if A is also false. If A is true and the right hand side is false, it's going to be false. So we know that A has to be false. Once we know that A has to be false, we can use the chart for disjunction. So one is A or B. This is only true and one of them is true. We know A is false, which means to make this true, B must be true. So we make B true. If B is true, if we make C true, then the second one is going to be also true. So this argument is invalid because we were able to generate all true premises and a false conclusion. So let's look at number 9. This is actually much harder than the other ones. So to make this conclusion false, we need to start by looking at the table for disjunction. A disjunction is only false when both halves are false. So we have B and C or A. So we need to make A false. And we need to make B and C false. So making A false is easy. Let's just make A false from the get-go. So if A is false, then premise 1 is automatically true. If we look at the table for conditional, that's going to be the case. If it's false on the left-hand side, it's always true. So now B and C has to be made false. B and C can be false when either B is false or C is false or both are false. So I think here the key is that we're going to want to look at the second premise. So the second premise has B implies C. So what we don't want is for B to be true and C to be false, because that would give us a false premise. So if we make B false and we make C false, then the second premise is true. Also, if we did that, the first premise is true and the conclusion is false. So we can show that this is invalid. Now, I'm not going to make you use the short circuit method. I do think it's much faster. But if you don't understand this method well, it's okay to keep using the other method in this class. So, I want to thank you for your time and attention. As always, this class depends on your participation and your questions. If there's something you don't understand, please ask me. I am eager to help you to understand this material. I look forward to seeing you in class. If you're doing this on the internet, please just ask me questions via comments. I appreciate any sort of feedback. Thank you for your time.